Hey everybody, welcome to Math with Ace, focusing on statistics today. We are doing an example on how to calculate a confidence interval for a one sample mean problem where we don't know the standard deviation of a population. And we're going to do this using technology as well as showing it calculated by hand. So the first thing to note is we have this big problem and we need to kind of determine what is important in this information. The Human Taxone Project is working to understand the scope of industrial pollution in the human body. Industrial chemicals can enter the body through pollution or as ingredients in consumer products. The scientists at HTP tested cord blood samples for 20 newborn infants in the United States. The cord blood of the in utero newborn group was tested for 430 compounds, pollutants, and other chemicals, including chemicals linked to brain and nervous system toxicity, immune system toxicity, and reproductive toxicity and fertility problems. There are health concerns about the effects of some chemicals on the brain and the nervous system. Table below shows how many of the targeted chemicals were found in each infant's cord blood. Great. Lots of awesome information about what this problem is about, its context. However, really the most critical part was we're dealing with 20. Now we need to use a sample to construct a 90% confidence interval for the mean number of targeted industrial chemicals to be found in the infant's blood. All of that is relevant and tells us the percent that we're dealing with, it tells us the parameter that we're estimating, and it tells us the context of the parameter. So what we need to do is head on over to Statlet, and we need to determine where are we going to calculate this. T distributions is for calculating the probability, and it's for calculating the T value. But if we just want to create the interval, we go to one quantitative variable single group. And this is chemicals in infant blood. And I'm going to enter the values of 79, 145, 147, 160, 116, 100, 159, 151, 156, 126, 137, 83, 156, 94, 121, 144, 123, 114, 139, and 99. I begin my analysis and I get to collect the information that the mean of the sample was 127.45. The sample size was 20, and the standard deviation of the sample was 25.965. I'm writing all of this down because when I do this by hand, I want these numbers. Now, if the sample size is 20, what's our degrees of freedom? Well, degrees of freedom are n minus 1, and 20 minus 1 is 19. That's going to help us later. I scroll down, and I get to see, oh, perform inference. Well, what kind of inference are we performing? Which ones look familiar? We're not dealing with sigma intervals. We are dealing with one sample for means, which is mu, and we're not doing a test, we're making an interval. So we're going to do a one sample t interval for mu, and we need to let the program know what level of confidence we have, and we're told 90%. I click perform inference, and there's my interval. So my interval was 117.411 to 137.489. Now we haven't checked conditions. We could interpret this and be on our way, but we do need to check conditions. We'll get there in our next session. We're going to talk about how we perform inference appropriately. But right here, we have our interval. Let's prove it by doing it by hand. But in order to do it by hand, I need some information. I need to know what is the p-value associated with alpha over 2, and how do I get there? So to find the t-value, I need to go back to t-distributions. P of alpha over 2 means I need to know what alpha is, and I work backwards through this. So the confidence level is equal to 1 minus alpha. So that means that alpha is actually equal to 1 minus the confidence level. And if the confidence level was 90%, as a decimal, that's 0.9. So 1 minus 0.9 is actually 0.1. So alpha in this situation, if it's 90% confident, then we have 10% for our alpha, which is actually how likely we are to make a type 1 error, which we'll get to later. So taking alpha over 2, 0.1 divided by 2, I get 0.05. So this is t of 0.05. So what I need to do is I need to find the area of 0.05 on the outside of one side. I don't want to calculate the area here. I need the value that goes with it. Our degrees of freedom were 19. And remember, I said do the right tail so that you get the positive number. So 0.05 to the right gives us a t value of 1.729. So that's the t-score that we're going to use to swing left and right on this problem with our point estimate. So let's do this by hand. We know that the formula for confidence interval is the point estimate plus or minus the critical value times the standard error of the statistic. Our sample mean was 127.45. And we just determined that the t critical value that we want is 1.729. The standard deviation of the sample was 25.965. And the sample size was 20. So again, if you're going to do this in your calculator, I would recommend making sure you're using either a graphing calculator or you are following the order of operations appropriately. This middle portion, or this standard error, is 5.806. If I multiply that by 1.729, I get 10.038. And now I can create my interval. I do the point estimate minus my margin of error, and I also do my point estimate plus my margin of error. Two separate steps. 127.45 minus, and I'm going to do this without rounding so that I can be as accurate as possible. I get 117.411. Shocker. That's what we had. And then I add the point estimate to the margin of error, and I get 137.48. I get 8 in my calculator rather than 9, which is what Stapley gave us. Being able to interpret this is key. So the way that we would say this is we are 90% confident that the interval 117.411 to 137.488 captures, what are we talking about? Mu, the true mean number of targeted industrial chemicals to be found in an infant's blood. Okay. Now, the population value, like the actual mean number of targeted chemicals, doesn't change. So we either captured it or we didn't. Okay. We're not saying that it's between these values. We're saying here's our values and we either got it or we didn't. So just know that the way that you word this is really important. So we're 90% confident that our interval captured it because the value doesn't change for the mean and we either got it or we didn't. Okay. Come back to learn about how to perform inference appropriately, checking conditions, and performing the calculations. Thanks for watching.